I'd like to welcome you to the session. My name is Keith Parris, and I work for Software Houses. And, when the bootcamp organizers were gathering sessions, they asked for sessions that were aimed at newcomers to OpenVMS. I don't know if we have any newcomers to OpenVMS, but this will be an introductory level. Sometimes it's good to go back and review things. I know I went over to I've done nuclear sessions, RMS, level. I still learn things that hopefully you'll be able to learn things as we talk today as well. Welcome to ask questions. So, introduction to OpenVMS Clusters. My brother works with Windows, and a while back he asked me, Keith, I know you work with VMS. How is it that VMS is still around after all those years? It's such ancient technology. And so to describe sort of the strengths of VMS, I said, well, we can have a cluster of servers all connected together. I can log into any one of those servers and I see the same environment. I see the same files. I can run my programs from any node. It really doesn't matter which one of those it's on. If a node goes away, then it's over. If I need more capacity, you have one of those. So this is one of the strengths of VMS, that the user environment is the same regardless of which node. And he said, yeah, that would be handy. I can see that people would still be wanting to use that. So outside, looking in, the cluster appears to be a simple system. You can have scalability by adding nodes, removing nodes. I worked with a company that was just rapidly adding nodes during the .com boom because they were brokerage, and VMS allowed them to scale by just adding additional nodes. And then the .com bust came, and they did it in reverse because they were able to turn machines back in under lease and eliminate the expensive nodes. And so it was just as good for scaling down. It wasn't a feature of VMS that I thought about, but it does allow you to scale back rapidly for economics that's necessary. And of course, users can move from a failed node to another node. They'll be able to service all their files from there. It's from there. VMS clusters have wonderful redundancy on a variety of topics. You have nodes, you have cluster interconnects connecting nodes, you've got network connections, SAN connections. This data can be replicated to protect it against failure. And this isn't just a matter of 2x redundancy, mirroring two disks, having two nodes in an active passive failover mechanism. We often can have many multiples of levels of redundancy. So you might have 3, 4, 5, 6, 7 things that are enabled for clustering, and it all works automatically. Shadowing allows up to 6 identical copies of the data. And the design actually supports 16. So if you ever wanted to, customers said, I need 16, because I'm reading a lot of data and a lot of copies of data replicated, they want to support it. But right now, there hasn't been any rationale for more than 6 or even 6 copies of your data. And if 5 of them fail, you still the MSCP disk server allows a node to continue running, even though all of its SAN connections failed, maybe the switches to which it's attached to failed. It can access it through the network from other VMS nodes and keep accessing the data running. VMS also has automated failover and failback in most cases. If a user's connected and they get disconnected, they can manually. If they're coming in from an external web browser, a service that can be completely transparent. In cases of program connected, VMS can fail over between different things automatically and fail back, add them on the fly. Just works. So in most cases, VMS is able to do that transparently. Disks can all be shared between nodes, or you can have multiple nodes if you want to. Multiple systems can share and boot from a common system disk. And this means that if you need to upgrade the operating system, you do it from that system disk. And you're effectively doing it for all of those systems within that system at the same time. So they have to separately install new software patches on all of the systems. So that can help you reduce your system manager, system administrator workload. It's a lot less effort to manage a cluster of 8, 10, 12 nodes than it is 8, 10, 12 individual nodes. In fact, it's not much more work to manage this single individual system. The cluster provides a common security and management environment. You can use the same username and password to log into any of the nodes. You can manage the cluster as a whole. The suspend utility is one example of the ability to do the same command on all the nodes. So you can log into each one individually. So it's a common security and management environment. We have a quorum scheme that protects against the cluster becoming partitioned. In other environments, they might call this split brain syndrome, where your access to the data is uncoordinated. That can cause the data. So VMS protects against that. VMS has a distributed lock manager so that it can coordinate access to all of those shared resources. So transparently reducing it at the same time. VMS is taking care of the arbitration and taking turns behind the scenes. It has a cluster-wide file system, so all the different nodes can get to the data, access it in a coordinated fashion. We're going to talk about today the system communications architecture, or SCA. We'll talk about interconnects. We'll talk about connection manager and its rule of global connectivity and the quorum scheme. We'll talk about the distributed lock manager and cluster server process. Those through the MSCP and TMSCP servers will get a brief mention, and we'll talk about support for redundant. So, an overview of the cluster. It is a set of distributed systems. In order to work together, they have to cooperate. In order to cooperate, they have to communicate. And so that allows us to provide information. This is the way that VMS clusters do their shared access. You've got users at the top. They may be running various different applications. They may be running on different nodes. The distributed lock manager allows them to make their activities transparently scenes as coming from these different nodes. And the basis of that is the connection manager. It's rule of total connectivity and forms. And that allows us to coordinate the fashion into the shared resources like disks and files and printers and files and systems. So SCA, that governs the communications between nodes in the VMS cluster. System Communication Services, or SCS, is the code that implements the SCA. One of the wonderful things about the digital heritage is that things are architected first and designed out. Implementations of those architectures. So it's a very organized and structured way of doing things that results in organizationally correct results. The terms SCA and SCS are often used interchangeably because SCS is the communications architecture. And that's the foundation for communication. Now, SCA has been implemented on a variety of different pieces of hardware. Early on, it was proprietary hardware, CI and DSS9. More recently, it's typically various different flavors of Ethernet. So that would be typically 1 gigabit, 2 gigabit. I'm sure the plans or capabilities, higher speeds as they are developed. And you can also form a cluster over an IP network, but you typically connect to those through, most often through Ethernet connections. Fiber channel storage area networks are sort of the sweet spot for storage at the moment, although this week about iSCSI. It's another option that would just get in and work once VMS supports that. Also have SCSI or SAS disks. But you can have a background memory disk. Those are various different options for your storage. You can, of course, use NFS and things like that as well. So, quite a few storage options. In the system communications architecture, each node needs a unique SCS node name and a unique SCS system ID. These identify the ports. The SCS nodes are more friendly to humans. It's also used. In order to prevent one node from overrunning another node, if traffic is controlled in its flow by grids. These are the 4 layers of the system communications architecture. You have the sysapps, SCS itself, ports, and we might look at it this way. Sysapps are called system applications, but don't be fooled by the word application. It has nothing to do with it. It's part of the operating system. It's just the way it is. You've got the SCS code itself, a port driver, and then physical interconnect over which you can send this data. SCA over LANs is provided by the big data projects driver. It's because it emulates the CI ports or the SSI ports that were there before and gives the same capabilities of LANs. It's completely more emulator. That's where we get the new DE driver. SCA over local area networks is referred to as NISA because NI was the digital name for this new networking technology called Ethernet. So you had CI, computer cluster interconnect, you had NI, which was the name. That's what they did. So the NI flavor of this is basically SCA over local area networks. We can also do SCA over IP networks thanks to IPCI, IP cluster. Basically, we're sending IP packets over using phone drivers. Okay, here's the layering. Within the port-to-port data layer, you've got a port-to-port driver and port-to-port communications. Transport is the layer that handles things like missing packets, retransmission, making sure that packets arrive in the same order. And then channel control would be associated with making connections to nodes, maybe over different mix. And then datacram exchange is just firing the packets. Letting higher layers deal with duplicates, reordering, sequencing, retransmissions, and that's it. You may be acquainted with OSI 7 layer network. And so it can be kind of helpful to compare that with the SCA model. Basically, in the OSI 7 layer model, you've got all these different layers. But down at the network layer, you've got a routing layer. SCA doesn't really have a routing layer. Now that we can do IP communications as a cluster and we can take advantage of routing to do that. But in the original SCA, one node cannot route packets from packet. No. So you've got to have a direct connection between nodes for some path. Today, that path could be a routed network, but originally it's just got to have a direct connection and not depend on some other node to be able to reach third. So SCI has no built-in routing layer. They can't route, like I said. You can bridge the NACI protocol. Now, because multiple independent clusters might be on the same local area network, each cluster is assigned each cluster group. So as a system manager, you pick one of those. And then there's also a cluster password that is provided. It's not so much a security thing as it's preventing errors sort of thing. It doesn't help in terms of encrypting the data or anything like that. It's just sort of an extra safety feature that if two system managers independently happen to take the same cluster group number, like one, but the odds are that they'll pick different cluster passwords. The two clusters will then report errors when they get a packet. So that'll show them the error. VMS clusters dynamically probe and adapt to maximum packet size. Dick is the one to make sure that this actually happens correctly. That means that if your network folks all of a sudden decide to allow jumbled packets, the driver will be able to then take advantage of that dynamically on the fly without having to change things. Just propose with large load packets once in a while to see what it can actually get through them. And if your network folks conversely disable jumbo packets on something, the VMS cluster will automatically have to do that without you having to, so that it's flexible and can deal with the environment for what comes. So you can do jumbo frames on OpenVMS clusters may be presented with several different possible paths to get to a remote node. It's going to try and pick the best path or set of paths to use at any given point in time. It's going to try to avoid paths that tend to lose a lot of packets, because that's not a good thing. It's going to try and prefer the paths that have the largest possible packet sizes. Dick was telling me that IPCI path, which would be slightly shorter because header taking the packet capacity, would be treated the same as a land power, because they're essentially equivalent in terms of their capabilities. But if you've got a path that has jumbo packets capable, then for the packet path that can only handle the standard 15 byte packets. And also, it tends to avoid paths that tend to have relatively slower latencies than other paths. Sort of dynamically damage to the changing network conditions. SES flow control is based on credits, as I mentioned before. Connections start out with a certain number of credits, and as you send a packet, credit, publish it back, helps increment your credit back up. But you can end up with case where you've got to wait for credit to occur. There's a sysgen parameter called, yeah, just on the next slide. Cluster interpreters. So SES provides reliable report communications. It will send data between a node and a virtual circuit, and there are connections, multiple connections with virtual circuit purposes for communication between those two nodes. And I did like every other person and everything back there. All right, so virtual circuits are formed between ports on a cluster and connect to something. And there can be a variety of different types of connections that run through that same virtual circuit purposes. Virtual circuits can pass data in three ways. They can send datagrams, which are basically just fire and forget. No guarantee it gets there. Could get there twice, 3 times. Could get there out of order. And then sequence messages, which are carefully controlled so that they only get there once. They get there in order, and if they get lost along the way, they'll be still. And then block data transfers, that's used for larger amounts of data. Maybe if you have an MSC served disk, send disk data that way. So, datagrams, fire and forget, no guarantee. It's a high probability that it'll get there, but no guarantee. Might be out of order, might keep this. Maximum size is typically fairly small, 576 bytes controlled by SES maximum. It's a sysgen environment. And we use this for polling for new nodes. PD driver mellow packets, datagram going across. We use it for forming the virtual circuit sequence the nodes. Interchange that the nodes do to form a new virtual circuit. And we also use it for logging asynchronous errors. Sequence messages guaranteed, delivery, nothing lost, or the virtual circuit has to be closed. First in, first out ordering is guaranteed. It's maximum size. Last I looked at SES max message was 216 bytes. That's basically sort of the size of a block list. So as field widths increase to the cluster version number has to increase some of those. We use those for things like walk requests, MSCP IO requests, MSCP message saying that the request IO is successfully, that sort of thing. Block data transfers are used to move larger amounts of memory from one computer system's memory to the computer system's memory. And it would be things that would be larger than the 216 bytes. 576 bytes for data. The data is mapped into named buffers on each end. They specify a location and size in the memory you're transferring to it. You can either initiating send data or initiating requesting data. Just to tape data transfers are probably the most common. We also use this for, since 7.3, we use this for clock trigger mastering clock as it's efficient. And we also use it, interestingly, for OPCOM messages. You don't think of OPCOM messages that have 32 bytes or something. We use block data transfers for those. SysApps. Okay, as I mentioned, although they are called system applications, they have nothing to do with users or business applications, but they're parts of the operating system. Work in pairs, one in each node of each. Communicate, connection, circuit. And although they have nothing to do with this process, names each one. The CA architecture is given a process name. That's not a process. So we have VMS $Backs cluster, which talks to another instance of the same sysapp VMS $Backs cluster, and that implements the connection manager communications for other purposes like the block manager. Cluster-wide process services. Those allow you to get information on processes on other systems. So start or end processes. Other nodes of the cluster. These were written by a gentleman named C.W. Hawes. So we suspect that the name CWPS was because it was C.W. Hawes Cluster-wide process services. I don't have any actual proof of that. VMS disk class driver talks with sysapp MSCP disk. So that would be the driver on the left talking to the MSCP disk server to provide remote access to disks. And we have similar ones for the teams. SCA transport was a block data transfer sysapp pair that or sysapp implementation that was used for VMS cluster environments. So there was an inter-process communication service in cluster-wide that the key manager uses that in DECT. But there's a new IPC that uses different mechanisms. SCS $_lookup is used to see if there is a particular sysapp line and talks to the SCS directory sysapp line. So those are some examples of systems. Connection manager. Connection manager is code that implements cluster membership, that sort of thing. So it'll handle forming a cluster initially, allowing a node to join that existing cluster, cleaning up after a node has failed of the cluster. And all the while it protects against uncoordinated access to shared resources. Now every system, according to the rule of political connectivity, has to be able to talk directly to every other system. So transparent LAN bridges, you direct to PAM, both from the same LAN, each other, all packets get back and forth. It's a direct PAM. Or if you get through an IP network, that's considered a ring methods. Now, if the rule of total connectivity ever gets broken, that is, some subset of the nodes cannot talk with some other subset of the nodes, we need to fix that and restore the rule of connectivity. So we're going to have to adjust our cluster membership. That might mean throwing out nodes that can't talk to other nodes because they have failures and whatnot. That'll be what's called a state transition. But in any case, this state transition will bring us back to a state where we have the rule of total connectivity back once again. Connection manager also enforces the quorums. Quorums team ensures that access to shared resources is coordinated, kind of like the U.S. Senate had a majority of votes for pass. That's why the government still shut down. Okay. Well, your cluster will be shut down if you don't. So a majority of the potential cluster members must be present and able to communicate, or any access to the shared resources is allowed. When I was living here in New Hampshire, we had a school, a small private school that had a school constituency meeting that they regularly held. But it was hard to get people to turn up to the meeting. And so they proposed, let's change our quorum. It's lower, an easy fix, because we don't have a lot of people come out with this to lower our quorum. Coming from a VMS cluster environment and background, I knew that this was not a state to be in. So I warned them, do not lower your quorum, because if you did, that means we could have two conflicting groups meeting at the same time, making conflicting decisions about your school. And they said, oh, so they didn't lower their quorum. Same is true in VMS cluster. Sometimes systems, or sometimes disks, are assigned some number of votes, and they can contribute to quorum and make it easier to achieve. The total number of votes that is possible in the cluster is called the expected votes. And that's the number that nodes need to know when they're voting to know that they're talking with the majority of cluster members. If you artificially set that to no, they might talk with a subset or a cluster, gain access to this cluster. So you don't want to set expected votes on your systems such that it's lower than what you're expecting to be there. That's an unsafe condition to be in. Quorum is defined as a simple majority, so just over half of the total possible experiments. Now, in the event of a communications failure of some sort, so nodes can't talk to each other, systems within the minority will voluntarily suspend their processing while systems in the not part of the quorum. VMS prevents it from doing harm, so it's voluntarily keeping its hands off of the disks, basically. So it puts all disks into non-perfect state. It requires that any processes that ought to be scheduled can only be scheduled if they have the quorum capability bit set. And at the same time, it takes the quorum capability bit from away from all its use. So that means that no processes can be scheduled unless they were, unless you're doing something very, very. So normally you can't run a process lost state. So that prevents you from machine codes, prevents you from in suspense until we find it. Now, for cases where there are even number of votes, the U.S. Senate with 50 in each summary total, you can have a tiebreaker. That can be a tie-breaking vote, or disk, or no, or if you've lost one, there's no way that the nodes will come back because they just failed. But you need to be able to continue and use the system manager to know that a subset of the systems will be safe to allow to continue. And you can take action with the system console that you press and tell it with human intervention, it's okay for you to continue. The console would do like a control meeting, do a queue just one. So that's a way to overcome quorum loss. There's no way to bring those back in. So you can have a quorum disk providing tie-breaking vote, have a quorum node tie-breaking vote. Sometimes people will desire to be able to boot any or all systems on a cluster. Make it simple. They didn't want to worry about one. So the way to do that is to set the quorum disk up with one less vote. If the quorum disk is then the total of all the votes, and that achieves the total points. As long as any single system boot up and with the votes from the quorum disk, they'd be able to be over half of votes that they can. The other thing it does is if the quorum disk would fail, nodes, since they have slightly higher numbers of votes to it, they can continue to run without the quorum disk. The quorum disk could be assigned votes. The way this works is VMS periodically writes cluster membership data into the quorum.dat file. Disk. And other nodes will periodically hold that as well. And as long as your picture of the cluster, as far as what you see, matches what you see coming from the quorum.dat file, as well. But if two subsets of the cluster cannot communicate with each other, then they'll see different records written to the quorum.dat file, and they feed it back, and they write their version, sort of arguing over the quorum.dat file contents. The nodes know that they can't count the quorum disk votes safely, and so they'll refrain from counting these votes until that fixes where your clusters votes will get shut down or something. So that's a way of keeping them from counting quorum disk votes if they aren't the only subset of cluster access. Now, if too many systems leave the cluster, it'll say quorum lost, activity is suspended in the cluster. So from a system console connection, you couldn't fix that. Now, if two non-cooperating subsets were able to achieve, or maybe you build your node with the LAN connections broken, but expected to go set to 1, and you have access to the same, then you're going to be able to build a port partition cluster or split lanes. This could also happen if you standalone system with cluster have access to the same disks. If you mounted that disk, start doing IOs to it from multiple systems, then you very quickly resolve corruption on the disk, because each part will allocate files, but they don't know that space is only allocated. So you very quickly see, if you do an analyze disk, you'll very quickly see more blocks. That's a bad sign. It's not fun to fix those either. How can you avoid a partition cluster? Set expected votes properly. VMS is smart enough that rather over the cluster existing votes values for expected votes, which will match itself in cluster-wide value. But you need to go back and raise to put some of those typically be run with origin. Raise that. You can make vendor form adjustments. When you shut a system down, it helps if you use the remove a code option, because that tells the cluster, this is great work by John Colbert, tells the cluster, remove the effect of this node's votes as it shuts down. So if I have 6 node cluster, shut down to 5 nodes, 4, 3, 2, 1. If I always use the remove node option, I'm going to do. So that can be another thing. Sometimes people will do a conversation to temporarily lower expected votes. Let's say you have a 5 node cluster, so expected votes is 5. And you want to get the cluster up and running, but if you leave one node, it's going to say, okay, here I am. Quorum is 3 out of 5. 3 is majority. I don't have enough votes, so to sit around the next node, send 2 of them on top. But we still don't have 3 votes. It's within the 3rd node. So I said, okay, now we can actually start doing something. So people will often do a conversational group, set expected votes to 1 with that first node up and running. But there's another sysgen parameter you should use called write sysvariance. You should set write sysvariance to 0. That means that when the node comes up all the way, it will not write that value of 1 for expected votes into the current sysgen parameter set. It will leave it at the original. That's good because that gives you safety of that node unexpectedly reboots to be reading proper that we have to quotes from the session current parameter file. See. All right, some communications failures are temporary. Sometimes we don't even know what's happening with this team for some period of time. We're unable to move between those. So to prevent that from immediately causing a problem, we have something called reconnection. And this is the notable time where the cluster will wait patiently, hoping that the communications will be restored. If communications haven't been restored within reasonable interval seconds, then you're going to take some action. You're giving up on the communications with the other node. You have a cluster state transition where you throw out the node and continue with a majority of the votes. Or you may have to hang due to performance to fix the communications problem until it's fixed. People will often have clue exit bug checking, and that's typically when a node has been trying to communicate, and then its communications are restored. It talks to the rest of the cluster. The rest of the cluster gets that news. We have been removed from it. What it means is that all of the blocks that we have cannot continue. So it does a clue exit bug check to exit the cluster, reboot back into the cluster, and then it will be able to once again cooperate. All of the locks that are held in our history, but we can start over the process. All right, this reconfiguration is called a state transition. Those are typically removed from the cluster. If you have communications between a couple of subsets of the cluster, the cluster will evaluate which part, if any, is able to continue. If there's a part that has one, then obviously can throw out the other nodes and continue processing. So VMS is going to pick the subcluster, first of all, with the most votes. It's not the most nodes, it's the most votes. And sometimes the number of votes in both of the subsets of the cluster are too high. So then it's going to add in the factor of the numbers of votes and trying to keep the most votes up. Sometimes the number of votes and the number of votes are too high. In that case, it's going to compare SCS system ID values. And that set of nodes with the most recent cluster software version, pick one of those. That becomes pretty arbitrary. It's deterministic, but to you as a system editor, it's pretty arbitrary. Let's talk about the distributed loss manager. This is how we can coordinate access between different nodes on the cluster. So those resources might be disks, might be files, records within a file, buckets within a file, might be tape drives. Also, internal operating system cache buffers, things like that. Physical resources get mapped to symbolic resource names. So this is not a matter of you taking a quantum of physical resource. These are all symbolic, and you follow the rules. It's all architected. As long as you follow the rules, everything is great. There's nothing to prevent you as a privileged user from being there and bypass the law. That's your own fault. You don't commonly see that. Value, sharing, abilities. So you take out blocks of these symbolic resource names that stand for you. We've got a system service enqueue to take out a lock, dequeue to read a lock. So you can do new lock requests, existing lock requests, granted, you can release locks. There's also a system service called get LK9 that allows you to find out lock information. What are the existing locks that are held with the existing resources? So physical resources are protected by locks on symbolic names. And these resources are often arranged in trees. So for example, you might have a lock on the file, and within them, a sub-block on a particular data bucket within that system, and then a particular record file, like the sublock of a file as well. Different resources are coordinated with separate resource trees. They're carefully designed so that they get as much contention as possible. Here's some examples of symbolic resource trees. If you see a lock with SYS dollars, something that's a lock used by the Linux executive. If the prefix is F11B, that would be the SPG of the file system. RMS dollar is the prefix for a long tree for RMS file. And you can find in the appendices of the internal data structures books what these formats are for this. Here's an example. The device lock has SYS dollar sign, followed by the device name text. That with a show lock command, it's very easy to tell which device that is a lock for. An RMS lock tree for an RMS index file is a little harder. RMS dollars. Then you have the file ID. File ID figure what file it is on that. There's the flag slide as to whether the disk is mounted by the share. And then there's the block value name, which is the volume name at the instant that it's mounted. It stays constantly through the system to change the volume. So then you can identify the file specifications in the file and pick up the volume name. But this would allow you to tell what file this is a block for. And then subblocks of that top level block would cover buckets and records within that file. So here's an example of the structure of some arbitrary RMS index file. We've got a root index bucket, level 1 index buckets, level 2 index buckets, since this one is a large enough file, and then some data buckets that link to. So when you want to access data, you go to the root index bucket that would compare the key with what's in there. That will take down one of the other branches of the tree until you actually get to the data within the data bucket of the record. Within each data bucket, and so you can lock individual records to that level and still coordinate your access down below the records within. Different types of locks allow different levels of sharing, exclusive access. You can have protected write, so you can write it, other people can read it. Exclusive means don't even look at this. Protected read allows reading, and other users can do it. Concurrent write allows writing while other people write. Or concurrent read allows reading while other write. So we don't care if somebody else writes it, but it. And no, I think I'm going to use this again in the future, but I don't have any right to do it at the moment. But I've got a handle to it. I can change it perfectly. So locks can be requested, released, converted. And here's a compatibility map of which modes are compatible with each other in modes. So anybody that has a null lock, share that lock with any other null lock. It's down into various different degrees of sharing. If somebody has an exclusive lock, then null lock is the only other thing that can exist on that resource. VMS assigns a single node in the cluster at a time to keep track of all of the blocks on a given tree resources. And that node is called the lock master node for that particular tree. Different trees have different nodes, and so lock master nodes. And VMS will kindly, dynamically move the whole lock tree around the nodes so that it tries to keep the lock tree on the node for most activity. So it will remaster the tree to a different node so that access to that will be most efficient. So you may see lock trees move around. Maybe we run a backup over here and then we put some lock trees and to the disk over that node temporarily, and we move back to your application because we're going to do that. Works pretty well. So here's an example of distributed locks So we've got node A, which happens to be the lock master node for whatever resource tree starts with X. So it keeps track of its own blocks on resource X. So I have a block on node A. And then node B might have a block on resource X also. So the block master node keeps a copy of that. Node B keeps a copy of that. And then node C might have a block. Node A will keep track of them as well, since it's the block master. So you can sort of see how that works. The directory lookup is how VMS finds out which node in the cluster is the block master. Because theoretically, you can take out a block and find out which node the block master is. So the directory lookup is how VMS finds out which node is the block master. It's only needed for the first block to be best, because your resource block, if you already have a block on the resource tree, the resource block will tell you which node is the block master. Store that. Having to ask every time to take out a block. Basically, we take the resource name, cache it, we index it to the vector, and that points to a node that will do the block directly. This is an example of how that works. Maybe we've got 3 nodes in the cluster. I'm going to use the Goldilocks children's story as an example here. So we've got Papa Bear, who's big and powerful. Let's give him a block directory weight of 2. So it's going to do 2 units of block directory with this cluster. Mama Bear can have block directory weight of 1, so she'll be half as much as Papa Bear. Baby Bear would totally let off the book until they turn 18, at which point it's a little weight. So the resulting block directory weight vector have 2 entries for Papa Bear, 1 entry for Mama Bear. When we hash the resource names, we'll index into this. And so roughly 2/3 of the Papa Bear statistically is going to do block directory work on Papa Bear. 1/3 Papa Baby Bear doesn't do any block directory work. Okay, when we do a block directory lookup, we do a user log request. We hash the resource name, figure out which is the block directory node. We ask the block directory node. It'll tell us what the block master node is. And then we can make the block request to the block master node. So that's the basic concept. So what are the latency of block requests cluster? Well, it depends. Is there a block directory lookup needed? Maybe we've already got a resource block, so we know where the block master is. We don't have to block directory lookup. That can be done. Is the block master ourselves? So that this node already knows the number of blocks on that resource tree, or is it a remote? No. That's true for both block directory lookups as well as initial blocks. A dequeue operation is easy because we just fire it off. Sequence messaging takes care of getting it there, guaranteed we wait. It's going to eventually be free and what makes a big difference in what request latency is whether we can do it on the local node, or whether it's the block master node, or if we've got to talk to some other node to get the request satisfied. And if it is remote, what's the speed, what's the latency of the internet to get to that remote node? So local requests are going to be fastest. That's why VMS wants to move from block mastership to the node of step 2. Then those local block requests. Remote requests are going to be significantly slower for several reasons. One is the code path. Not only do you have to do block manager code, you've got to go through SCS on the local node, create your packets, across, go through the PE driver, receive it in PE driver on the other end, go through SCS code, then you find the block manager, and then your return trip with the response has to go back to the same. So the code path is about 20 times longer lasting, and the interconnect itself is also contributes some amount of latency, much greater than memory latency, just using block manager. So the total latency can often be up to 2 orders of magnitude higher than the local block request. So what we see in current systems, if you make a request from a client to the local node being the block master, 1 to 3 microseconds is typical. If you're having to go across maybe gigabit Ethernet, it might take 95 seconds to do it instead of 3. So that's part of it. It's almost a quarter. It's a couple hours. So here's some measurements I made on customer system recently. Local lock requests were 1.4 seconds. Going over 10 gigabit Ethernet, 1 gigabit Ethernet about 99 seconds. Now 10 gigabit Ethernet is not really 10 times faster, even though the bandwidth is faster, but it is enough faster that if lock request performance is important in the cluster, taking advantage of the faster internet is a good thing. These are examples I got from a customer. They already had 10 gigabit hardware in the systems. It's just that because their mentality was that of Unix clusters where the cluster interconnect is only a target, they configured 1 gigabit instead of the 10 gigabit for the hardware for. And I told them, why don't you use, all of your network infrastructure is 10 gigabit. Why don't you put your cluster interconnect? And they did, sure enough, all the hardware was down from 99%. Because the lockmaster node keeps track of all of the locks and all of those keep track of their locks, that gives us resiliency against a node failure. If the lockmaster node fails, VMS will pick another node as the lockmaster, and all the nodes will tell that node what they know about their own locks, and you keep on going without failure. And if any node fails, the lockmaster node just frees up the locks from that node, then moves the cluster and can continue on. Scalability, because at most we do true lock requests. I mean, we do a lock request, we look up, and then we do lock request itself. At most, we only have to do 2 remote operations, regardless of the number of nodes in the cluster. So that makes it scale very well. Whether you've got a cluster of 2 nodes, or you've got a cluster of 96, or 3 on the Envision 205 or 256. So it all scales the same. At most 2 units. All right. And because the lock directory of lockmaster should be is trivial on the nodes, that helps move away any single node. So we want to get rid of all of one spot back. VMS distributed lock manager will also detect deadlock conditions, notify the application. Cluster server process runs on each node. It assists with things that need to be done cluster-wide, such as those things. The MSCP and TMSCP servers allow you to access remote disks and tapes across cluster interconnect. And VMS can take over from a direct send access to MSCP server access and keep your access going. Same with the failed template. I wanted to point you to some resources. VMS documentation is excellent. The BSI OpenVMS Cluster Systems Manual, the guidelines for OpenVMS Cluster configurations, and the OpenVMS Shadow Guide are all useful. There's a book called Next Cluster Principles by Roy Davis that has great descriptions of the internals of how clusters work. And it's kind of hard to get a hold of the physical copy of that book, but I found that if you Google his name and the title of the book, archive.org has a copy of the book. You can log in and check it out. So it's accessible if you can't get your hands on the physical. And that's all I have. I've been one of the time, so you're going to ask a question sometime. The next session starts in another 5 minutes. Yeah, 5 minutes.
So out of curiosity, PCI cluster.
One of the things that happened with PCI, I think I can be blamed for kind of casually VMS engineering to do this because I had customers that their network folks came to them and said, we're taking away your LAN bridging access and your longest cluster is going to quit working in here. So there was that pressure to do that. Something happened in the market that could not have possibly anticipated. VMware. VMware, the vMachine requires that the system be deposited into the same subnet so it can keep the same IP address. That means the IP vendors had to come up with ways to make it look like a transparently bridged network connection between sites, which also would have to carry cluster traffic. So I think because of those capabilities of the network switches, where they can do what looks like a bridged manipulation over something that's actually IP, they have been reason to see less next time. But I'm really glad that you've got it though, because now you have people coming up requiring encrypted completions. I think that's going to be this year thing to solve over Microsoft is over.
I would so this. For this customer.
Yes.
They use some cloud solution.
Yes, we saw Ethernet over IP boxes.
But how? It was like that. Some of us, just for us, cluster ownership.
Right. So what would happen is in those cases where you couldn't get a bridged connection, your packet would go into an Ethernet over IP box that would talk to the connection to another Ethernet over IP box, which would then broadcast as if, and the implementation then would just have to obey spanning tree rules as they pass the packets. There were a lot of clusters with their questions in Moscow where they didn't allow anything but IP traffic and not the formal sensor clusters with their terminal interface technology to get care of them. And Ethernet over IP boxes still exist. Last time I did a Google search, there was still better still. So, one thing you have to watch out for is the things sort of something called plates. Just layer two. They can raise your request is very high. 2000s searching. How many folks are new to VMS clusters? Nobody is new to VMS clusters. Well, relative. Well, I guess it doesn't hurt to go back to basics. Hopefully this was useful for you. You can fit a clever review.
For the next session, you mean the clusters that are spread, what was that like?
Right. And sometimes it's different data centers or other end of the fan, or sometimes it's different towns.
Oh,
It just
okay.
depends.
And,
But where they're
I see.
Oh,
The way you don't
I
like
thought we had
time.
another one. My timesheet reminder.
Yeah.
It sounded like we had what we got the other day in the hotel. Especially coming from that direction with the windows. Oh, yeah.
Thank you. We don't have multi-set, but we have split a cluster split across two data centers. I think.
Right. So what I'll be talking about will apply to what we can.
Oh,
It's just
so
we
I'm
don't
thinking,
have
should I stay here or go?
You can watch this on the YouTube app.
Okay,
Because your distance isn't huge,
it's not.
as big a deal as it would be. You know, if your distance was sort of
Right.
hundreds of miles. We do have customers where they're tens of kilometers.
Yeah, we don't have. Okay, thank you.
Sure. Yeah, so just watch this one on YouTube. Get your favorite session.
I just thought it was kind of interesting. I don't do a lot of clusters. Of course, I run into them occasionally, but the clusters I do a lot of work with VMS based. If you look out the RMS specific bits and the VMS specific facility names, You just gave a perfect presentation on Windows failover clustering.
Where
It's
did
almost
they get that
exactly
idea?
identical.
Where did they get that idea from?
I don't know.
That might have passed on a few hints.
So I got two anecdotes for you. When I first joined BMS from 20 in the BMS, I used to sit right across the aisle from Dave Teal.
Uh-huh.
I heard him say this 100 times. Damn, cool exit. I don't have a clue why we exited. I've never forgotten that because I heard him say it almost every day.
I think I better get the right presentation up here. That's
And I
good.
couldn't
That's
live
really good.
without IPCI right now. That's all I do. Everything I do is IPCI.
Interesting.
Just one, I don't have to know where the systems are in the lab and what switch is connected to what switch.
Yeah.
I run VMs on probably 5 different hosts.
Yeah.
And I got my file, I give it to every node, they load it into the DAT file. Bang, I'm up.
Excellent. Excellent.
Which is why I was asking the other day in the OCI about IP addresses. Because
Okay.
I got my 10 nodes, they've all got their IP addresses right now. How am I going to get a single address from Oracle that I can add to my list to get my cloud instance into my cluster?
Yes.
You're gonna say, yeah, we're all like veterans here, whatever, but I always love your presentations. They're fantastic. But, I'm sitting there going, wait a minute. That's such a clear and concise explanation. It's sometimes like almost in the left field, talking about the exact same thing. And I go, oh my, I really screwed that up. Nobody understands what I just said. And I got to go back and do it again.
I was hoping to get a lot of, room full of newbies.
Yeah. Although I think we're still kind of the guys about to retire field, so everything be around.
There's stuff that's new.
Oh, yeah. Yeah, it was really great. I appreciate it. We're gonna hang around for the next one.
All right. Now we're going to talk about VMS performance in site clusters. So the last topic was supposedly aimed at newbies. This one will drill a little deeper and show you some complex stuff. You can also, if you're interested in complex stuff, you can also check some of the YouTube sessions from the last bootcamp in Boston. Because since we had a bootcamp from 2017 on until then, sort of collected all the bits of what stuff was new. And shot by Maud at the last boot camps, all of those things. And then they said, this boot camp, we need something different. So look around at the corners. What did I even cover last time? Well, this is one of the ones we did not. Give us performance in multi-site. So what things can you do in a multi-site cluster to maximize performance with given the configuration of spreads, physical, geographically dispersed on the sites? The distance between sites will hurt you in 2 different ways. One is in terms of what remote displays, and it hurts you. Most displays will be a little slower too, but primarily writes. Write bitmap updates that are required for those basic mini merge to write bitmaps as well. And remote block operations in sites will also hurt you in terms of sites. What is the intersite latency? Well, the easy rule of thumb is to figure on about 1 millisecond for each 100 kilometers. Europe, Asia Pacific, and for those of us in the US who promised to go to the metric system and then failed because I'm stuck with the older units. That's roughly 62 miles. And I have a spreadsheet that I put out on certain websites and to calculate the latency. The highlighted cells you just fill in with the input values and then you calculate the output values. So if you put in the distance, it will tell you the latency. If you put in the latency, it will tell you the distance. And that's all based on the assumption that in premier sites you probably have dark fiber. And the speed of light through dark fibers are roughly 2/3 at 6 meters. Speed of light through that. Based on an interesting anecdote. In fact, you can look this up on the PBS website. There's a special called Speed that talks about. There were some people that wanted to give an advantage in stock trading knowing physics, they knew that the speed of light through a vacuum, or the speed of light through air is about 90% the speed of light through a vacuum. So they actually made a set of 20 towers between Chicago and New York so that their trades could beat the people that were sending their trades through the fiber optic general network. And that was the viable business model for them at that point, because they get in and get their stock trading just a little earlier, get their updates a bit faster because of the differences between fiber here. So somewhere between Chicago and New York, so microwave towers. The bandwidth was very limited, it was like 20 megabits. So that was enough to, the latency was what would happen early in that. Now, your actual circuit path length between the sites can be significantly longer because they've got to find a right way to take right to the right way to take a trench fiber. So that might be significant. You can measure it. Now, you can use a ping. If you have an IP network between the sites, you can use a ping. Small distances are the same things like 0, 0, 1, 1. So you get these very small values. Well, I really wanted 0.746 or whatever the lowest I could do. If you took enough of those samples in theory, you could average them all together and actually see much better resolution by averaging them. But ping does not have a very good resolution, so you can try to take a lot of these. I also have a tool called Lock. There's a gentleman named Roy Davis who wrote programs to measure things. So what he said, and so this lock time tool you can get from the Encompass website at Eisner.com. Tilde /tilde Parris give you the obvious. So you can grab that and procedure against the macro programs that don't have to build parameter or people want to build the programs and create sort of this. So basically that will tell you the lock request latencies between the two nodes. If you take the lock request latencies between two nodes of the same site, compare them with the latency between the nodes at two different sites, subtract the subtract the same site from the two different sites, you can actually get an estimate of your site latency. If you run it when your system's running, that's best, but just keep the lower value. All right, so it's going to create a CSV file and then load that into Microsoft Excel. So here's an example from one of the customers. So the from node names from the left, the two node names of the senders from this node. This is how much request took. You can view that as a three-dimensional matrix and then a three-dimensional graph, and what's much more interesting. As we look at this graph diagonally, the low ones in the center are the local one requests that are going to be fastest. They're a small number of beats of microseconds. And then the tall ones are the lock request latency between the sites. And then the smaller ones are the lock request latency between different at the same physical site. In this particular example, the physical sites were about 15 kilometers apart. But the circuit path ends up being about 47 kilometers, so about 3 times. Now, if you access disks at a remote site through a SAN, or you do it through the MCP server, remote writes typically take 2 round trips. And so the higher the latency between the sites, the worse that penalty is. Now, if your SAN supports either Cisco IO Accelerator or Qualcomm is now selling the Brocade branded hardware. If you use their fast write feature, STIP-FW, then you can do writes in one round trip. What happens is the local fiber channel over IP equipment basically lies and tells the system, yep, it's completed as soon as it gets the IO. And that's okay, because if the IO ever actually completes, then the higher level layers will be transmitted. It's a good way with it, but it will allow you to get the effect of writes in one round trip. So for customers that have long distance between their sites, cutting your disk write latency for shadow sets in half can be a significant performance benefit. Now reads just take one round trip because you're just requesting the data and get it back. And that's the case whether it's MSCP served. It'll be interesting to me to see how iSCSI works. So iSCSI be two round trips like fiber channel, or if it would be a single round trip. I'm just looking to do a single round trip. I don't know enough about the ISPs because of protocol to the it's fiber channel and SCSI, both SCSI protocols. So whenever somebody finds out the answer to that question, T4 fiber channel monitor data I found to be very handy in detective mode to figure out what the latency is between the sites over the SAN. So what you want to do is find a shadow set, find a list of what the shadow set is, and find pairs of disks that are in the same shadow set and look at the T4 fiber channel monitor data for those pairs of disks. And you can see the local response time versus the local response time. You can look at writes, which typically take 2 round trips, or you can look at reads, which take 1 round trip, or you can look at both of them and correlate it to make sure that you're getting the correct data. So here's an example from a customer system. So what you try and look for is these flat lines horizontally. This isn't a real clear example. Measurements, but you can see that on the bottom, the orange kind of goes across, and it's roughly 0.8 milliseconds. And then this other bar goes across, and it's roughly 0.58 milliseconds. So if you subtract the two, 0.58 and 0.08, you get about half a millisecond. So it looks like the round trip latency, since this is reads, the round trip latency between sites is about half a millisecond. That tells me that the circuit path length must be about 50 kilometers. Now we can double check this by looking at write data from the same site. Writes take 2 round trips. So it looks like a remote write takes about 1.15 milliseconds. And local writes are about 0.15 milliseconds. I subtract the local from the remote, I get about 0 milliseconds. So that confirms what I found on the read side, that the round trip probably takes around half a millisecond. So circuit path length for this SAN is probably about 50 kilometers. All right, since we know that remote reads typically take 1 round trip and remote writes typically take 2 round trips with others in the service. We can speed up shadow set copies, full copy operations between sites. If we put the shadow copy thread at their target site, that means that it can write the disks locally just across the local SAN. It'll take 2 round trips to do that because since it's local, it's very fast. And then it can retrieve the data as reads from the other side, which only take 1 round trip. Well, how do we do that? Well, we want to control which node the shadow copy thread runs on. You can do that by the dynamic syschain parameter shadow, which recognizes the copy. And I learned this trick years ago from Virginia Clancy. She was a disaster product system administrator in New York. She said, "Oh yeah, Keith, you just set shadow max copy to 0 on all the nodes where you don't want it, give it a generous value on the nodes where you do want to. Issue the mount command to initiate the shadow copy. And when shadow looks around to see the node to put it on, you'll see the nodes with the higher values of shadow max copy. Let's take it. And that's brilliant. So I've used this ever since. And then once the mount command has added the member to the shadow set, it no longer matters what the values of shadow max copy are. Return the original values at that point. The intersite cluster interconnect is important. The quality of that is important. It needs to be clean so you don't want retransmitted packets. I found that even though intersite with distance is going to dominate the latency, you're going to be able to give a slight advantage if you use higher bandwidth network adapters. The latency going through the adapter, this seems to be faster. We did get faster microprocessors inside the NICs because they're designed to handle 10 gigabit versus 1 gigabit. But for whatever reason, the latency through the NIC seems to be a little less. So using 10 gigabit adapters if they're available instead of 1 gigabit, lower the latency just slightly. But it's going to be dominated if there's much intersect distance, it's going to be dominated by the speed of light. You want to have sufficient bandwidth in your intersect link typically to perform volume shadowing full copy in what you consider a reasonable amount of time. And that will be different customers. Customers say, if we can do that, 8 hours, we're okay. This is requirements. Some customers, 3 days, just depends what their business requirements are, how long they want to survive without full redundancy, what's acceptable to them. Jumbo packets can help. They can improve the performance of on-trigger stream in the CD server. It's by reducing the number of packets and the numbers. If you have longer intersite different distances, you might need to raise cluster underscore credits to avoid SCS credit weights. Now, are you getting SCS credit weights? You may or may not. You can find this out 2 ways. One is by looking at T4 data in the mon.scs class of data. You'll see SCS credit weights, CR weights there. You can also use show cluster / continuous. You can add connections, CR underscore weights, and then add the clusters connections between the nodes as well as the credit weight field. And if that is high or all asterisks, probably. So if you relate, what I typically do is any cluster that I get my healthy little hands on, I usually just set cluster credits to 128 in there after reapplying. VMS engineering tells me that in extreme cases, that probably even override systems limits set it to then 128, but I haven't done that. That's not exactly. But I basically just set it to 128. Any cluster that I put hands on that just minimizes the chances of getting cluster credits. Okay, if you have SCP servings in place, you might have to look at, and it's in use, you might have to look at FSCP underscore credits or FSCP underscore buffer, and also increase those for good performance. Now, SANs also use credit based flow control. So if you have a multi-site cluster with significant distance, you might also have to worry about credits with the SAN. And the SAN vendors realized this, and last I heard, they actually charge you more if there are more buffer-to-buffer credits in their switches. But it'll be a license cost, and the hardware is already there. But they're charging you more because it's true. So you may have to pay a little more, but that can avoid the credit weight at the SAN level. PE2, we run across a lot of customer clusters recently that can benefit from PE2. I had more detail on this bootcamp sessions from this point. But basically, PE driver, especially in multi-site clusters with long distances, it may expect to receive an acknowledgement back from the packet, but because maybe the jitter in the network is larger than it's expecting, whatever the case might be, it may conclude erroneously that the packet is lost and retransmit it. And that wouldn't be so bad because you just see the but when it retransmits it also cuts its window size, its current window size back. And that goes back gradually to minus like performance. So PE2 tells PE driver be more patient. PE2 is units of 10 milliseconds. So some customers I've seen you set PE2 at 1, it takes care of all the necessary retransmissions. Other customers it's 70. It just depends on the customer side. I just tell them to start it at 1 and then go until you get rid of the unnecessary transmissions. Once you get to 5, maybe go by 5s. Once you get to 10, maybe go by 10. So the downside of having 2 files is if there is a real packet loss in the issue for our retention. So I haven't seen negative sound effects for customers that have set it to values of 40, 50, 60, 70. And it does handily take care of the unnecessary retransmissions. I put out on the Commissar site, eisner.deepest.org, and that should say /tilde Parris / because my name is Parris. It's under my account there, so I have a typo on the side there. But the command procedure is called Parris _ com.txt, so we don't make those systems excited about .com. And you can run that DCL command procedure and identify if you're seeing unnecessary retransmissions in your cluster, or if the retransmissions that you're seeing are due to actually lost packets. So run that for a while, see what it says. You can run that dynamically while you adjust the dynamic parameter B2 on other nodes, and when it stops seeing retransmissions due to unnecessary retransmissions, then you can stop raising to the network performance. In multi-sig clusters, you may also have to raise the peak driver maximum transmit window size. SCACP has the ability to calculate what an appropriate window size would be for your configuration based on the speed of your link between sites in megabits per second, the distance, either kilometers or miles, and whether you're going to speed things like MSCP serving, or in the more common case, you're just optimizing for performance. So here's an example where we calculate the window size. Speed equals 10,000 megabits. So this is a 10 megabit connection. It's going between two sites that are 30 kilometers distance. SCACP calculates that you should have an maximum transmit window size of about 1,024 for that. Now, if you still got window full events, maybe you could raise that even farther. For that to eliminate window full events between the two sites. And you can raise and lower that dynamically, but you do have to be careful that if you're raising, you want to raise the receive window size first so it can accommodate it, and then go back and raise the transmit window size. Likewise, if you're reducing it, you want to reduce the transmit window size first, and then once you've done that on all the nodes, you can reduce the receive window size to match. If you ever set the transmit window size higher than the receive side, then the driver can transmit more than the node get in what's been broadcast. So here's some examples of commands to raise or so let's say we started out with a default transmit window size of maybe 32 or 64. Cluster would raise the value on the receive side to 256, and then raise the value on the transmit side to 256. Then we wanted to cut back. Let's say we did this. This actually happened in a real customer site today. I set up to 256, then their network actually started calling packets. Parris.com is now saying that the packets were actually being lost in the network because for some reason the network wasn't able to handle that level of peak load as possible. So then I turned around and lowered it to the lost packets. So you would set the window size to 128 first on the transmit side, use that, and then you can use the receive side to match. Shadow set sites and read costs. Because shadowing keeps the member disks identical, it really doesn't matter from the standpoint which member we read from. When a shadow set is read, the way the shadow works is it adds the local key what this is that this to read cost, and then we can direct the read for that shadow set to the member that has the lowest or those two things. So with disks with equal read costs, what shadowing does is it just sends them to disks on sort of so it spread the lower costs. Disks. The idea behind having differing costs is so if you have a cluster that is multi-site and there's a large distance between the sites, then the reads can be directed to the relevant site and be much lower response time than so we know that across the distance to the distance site. Now, if you have sites that are close together, I was talking with the attendees here. In that particular case, their sites, though they're multi-site data center, are different rooms of either of those data centers, but it's relatively close. There's some disaster tolerance there because if a fire starts, it's going to take a long to reach into eventually both. Some of them actually because firewalls they retard so that fire and allow you to survive the signals. But because the distance is so short, it may not make any sense in their particular case to set different read costs because we can measure the latencies with high general function. If the latencies are indistinguishable, sites and two data sites, it doesn't make sense to send all of your reads to the site because then the queue links are going to be bigger, slower than the sites. Now, site numbers for shadow set member disks tell me which site that disk is located. Because I understand VMS can't tell the difference. It sends IO request, and the answer comes back, and the latency may vary, but VMS doesn't smart enough because the latency is higher, maybe it's a site. So you have to help it by giving clues and telling them. So you can use set device / site equals and give it a journal answer, and that'll tell this. This kind of the disk is a particular site. You can also assign sites to nodes. VMS knows whether the node is at the same site as a disk or at a different site. You can use the sysgen parameter shadow _ site _ ID, and that being set to a positive non-zero value will tell VMS this node is at that particular site number. And then you compare that with set members of the this to decide what to do. There was an old sysgen parameter temporarily in some versions for shadow _ site, but that didn't end up being used. So if you see that it's shadow _ site. Now, alternatively, before that sysgen parameter, you could do a set device / site equals some number, DSA, such and such, and that set the node site ID. Shadow set. So the sysgen parameter is much easier way to do that for all of the shadow sets. All right, now with different site ID values, the read cost values for member disks are calculated by VMS handler. If you have a local background disk, that's given a read cost of real. Makes sense. That's sort of the fastest disk. Yeah. Local SCSI or SAS or fiber channel disks are given a value of 2 if they're the same size. However, both fiber channel disks is given a value that is 40 higher than a local fiber channel disk. So got value of 42, so difference of 4. This would mean that you would have to have a local queue of 40 before you start sending some of the requests to the disk. Now, MSCP serves disks are even more than that. An MSCP server disk is given a read cost value of 501. So you'd have to have a read queue depth of 490 before you start to consider sending some. So it's like almost impossible to ever reach that point. And even 40 for a difference is pretty high and pretty much keeps on the requests lower than this. All right, so the decision of whether or not you're going to use different segment numbers and see the different performance results will depend on whether these default read cost values are acceptable for you, or whether you prefer to override them on them. Maybe you like the difference, but your site distance is so big you want to set huge default values. Maybe when your queue depth gets to 10, you want to start using, you might say, well, I'm running active passive, but not any load at the other side. Once it gets to 10, it's faster to set some of those reads clear across to the other side and back. And still get a better response time than adding to the queue. This one's gets kind of busy. If, like the customer I was talking to recently, sites are close together, they may not choose to use sites. Now, if you want to set customized read cost values, that should be the set device/read cost commands for every disk. And you have to, you'd have to do that for every the disks. You do that every time. So that's all right. Sometimes a notable experience with burst of reads is queued from one. With equal read cost values, you can distribute the reads across all the member disks if you want to lower average response times. But with different read cost values, though, these reads are going to be concentrated on the ones with the lower read costs. And only after the local queue linked to those disks rises, then they will start to send some numbers with the higher read cost values. Now, if there's a very small difference in read costs, when the local queue depth reaches the difference in read costs, all your shadow will start and some of the read costs disks. That allows them to maybe satisfy things. If you've got an active cluster in each side is getting the same burst of reads at the same time, then it would not make sense to send some of the reads across to the other side. It's also experiencing the same burst of reads. But if you're running active passive, it might make sense to get some of the reads across to the other side. Now, with large differences of read costs like the default, the local queue depth has to be very high before you start to go across to the other side. So here's an example. The local read to a solid state disk, this particular example, has a response time of 0.2 seconds. The circuit path length between sites is 30 kilometers, so about 19 miles. Round trip time between sites is about 0.3 milliseconds. This is going to be additional overhead for those remote reads, because it's going to take some 3 milliseconds more to go over some sites. In this case, remote desks are accessed via standard SAN. The remote reads take round trip, about 1 trip, is like 3 milliseconds. And then, of course, you've got to go to the actual disk itself, 2 milliseconds. Total of 0.5 millisecond for the disk if that disk is idle. So when the local disk queue length rises to 1, we've got the next local disk read gets added to it. So it would take 0.2 milliseconds times 2, or 4.4 milliseconds if the queue length is 1. For the second read request. A third read request would have to be placed in the first read. So it's going to take 0.2 milliseconds times 3, or 0.6 milliseconds. Now, at this point, if the remote disk is idle, it makes more sense to start to send read requests across that disk, because you'll actually be able to get an answer from the script, despite them to be intersecting. So in this case, the difference in read costs of about 2 may be appropriate for the intersecting. So we might set the read cost as a remote disk to 4 instead. All right, so you can bias reads toward the local disk that allow the freedom to send some requests if things get real. Now, something that shadowing is write bitmaps. This is another performance issue on multi-site clusters. When you use host-based mini-merge, before a shadow set write occurs, shadowing will first update the associated write bitmaps when that should be sent. Now, there are some exceptions. It does a little bit of caching it that it keeps the little write bitmap, and if you've written to that area recently, since the last bitmap reset, it won't do the write bitmap update if it's already updated. Now, write bitmap update on a remote node occurs either site latency. And write bitmap updates, unfortunately, you have to do them on different nodes. you have to do it serially. Was at the time VMS was able to do them all at once. Got some strange data corruption issues that were unexplained. Root cause was never found, but they did find that by serializing right-bin updates that the problem went away. So I'm hopeful that someday we find out what the actual problem was. So that updates could be done in parallel again, but in the meantime, they're done serial. So the number of right-bin updates that we have, the number of those that we without will affect your performance. If there are, let's say you have a 6-node cluster, 3 nodes per second, you don't pay any attention when you set up your list-based bitmaps, and it takes the default of counting to 6. So you've got to write bitmap on every one of the 6 nodes. Okay, you're going to update 3 at the local site fairly quick. But at the remote site, you're doing 3 serial trips across the site. We had a customer that was doing, they had a 4-node cluster and they hadn't changed things. They were always using 4 bitmaps. So by cutting the number of remote bitmaps from 2 to 1, that sped up their remote writes nodes they were additional. All right, by default, HVM policy allows up to 6 right bitmaps. That could be allotted to seconds or the median. You need in a typical cluster at least 2, because that allows you to survive in the failure. If the node fails, it takes down its right bitmaps, you stop another node, and then VMS will automatically set up a second right bitmap to replace the one. If you have a disaster tolerant cluster, some people want to have 2 right bitmaps per site, so that if there was a site, there's some redundancy. But another way to approach that, if you're dealing with performance issues, is you might want to have 1 right bitmap per site. You can survive the loss of a node or loss of a site that way. And then, as part of your recovery procedures, inherent in site failover, change your host-based converge. You might have to change your host-based converge policy to then have 2 right bitmaps at the surviving sites once. So I'm saying, please add quickly a second one time for your understandings. Reset thresholds. This is something that's it's problematic because it's a case where a value is picked that stays constant as it scales technology. Disk sizes just continue to grow. It's amazing. That's why we make terabyte drive for personal for less than $100. And reset thresholds like this. When the product was based in where it first came out, the default value for reset threshold was 15,000 blocks. Later on, it was raised to 1 million blocks. So 1 million blocks is still compared with most disks these days. What I recommend is you set it to a percentage of your disk size. If you have different size disks, that will mean setting up different host-based converge policies. That's okay. I can read them. It's not too hard. If you set the reset threshold, let's say to 5% of the size of the disk, what that will mean is when you have node crash and you have to do a reconversion, it will, worst case, take about 1/20th time. And if you set the reset threshold to 10% of the size of the disk, then worst case, it would take 1/10 as much time. So you can just decide how much pain worst case take. Now on the average, that's worst case. On the average, it half that. At the time of the failure, right, that might have been 50% populated. It might just reset. It might be completely full. On the average, half that. But worst case, you can determine by the percentage what the worst case range time would be. I'm thinking that somewhere around the 5% range is probably optimal for a lot of customers, which is still 20 times the spaces. If your tolerance to merges is very, very good. So, I wouldn't think it would be default. This T4 has HBM data. It has a little bit of like but if you look at the HBM data, you can see how often you're doing a reset. Some customers, okay, they're doing a reset every couple of minutes or every minute, just because the reset threshold is set so low, the disk is large, and they're vertical. So consider sizing those to be the size of the actual disks to get so you're going to be creating the recovery time and the overhead of doing things. The other thing recent occurs is the process of the channels of control. Cluster rate. If your cluster is active and passive, that is, you have a node or a site or site that's not getting much work, consider setting cluster rate on the passive side to 0. So that way you don't get oversight block directory lookups, because there's no participation in the directory vector. Directory work from the site when you notice the kind of block rate set to 0. Another technique people can use if you want to do that, you can take out a poll with a program, just hold it as long as the just have the program go to combinations. And pull a block on the root resource, all block on the root resource of the block tree that's very important to you. That you're getting a lot of block directory reference. If you hold that locked, the resource block telling which node is the one master is there in the block. That's to the site. In between sites, those block just can hurt because they're very good on that. And some applications are not smart enough to take out a lock, convert it to some node, convert it back to one, and convert it back up. Some of them just take out your locks and free them, and then you lose your resource block and the record. So this is the way the kernel program can take out a lock and won't affect the performance of the operation, but it can keep that resource block around so you know. We've got a customer with disaster tolerant cluster site, and they wanted to set cluster weight to 0. That is passive, but during the DR test, they need to switch roles on the active site to the opposite site. It is possible actually to use the SDA extension LCPA to change cluster weight on the fly. So in that case, they change cluster weight passive. Change the passive of an active 0 to passive, and then they can do that switch for their humor tests without having to do normally cluster weight is not dynamics exchange. So I wanted to point you to some documentation of resources on clusters. The VSI documentation is excellent. The VSI OpenVMS Cluster Systems Manual, the guidelines for OpenVMS Cluster applications, and the VSI the shadowing guide are all excellent. There's also a book that gets into the internals of OpenVMS clusters, written by Roy G. Davis. It's a little hard to get a hold of a physical copy, but I did a Google search recently. His name, book title, and it did show a few copies of some reviews on book vendors. They're a little precious, but swing for it. Or another link that will pop up in that Google search is archive.org, where you can check out a copy. Thanks to the vendors and technology. So those are some good resources. And at this point, do we have any questions? You got to find something.